Right, hello everyone. Let's start this part 2 of chapter 6, the second law of thermodynamics. In this part, we are going to talk about the concept of heat pump or refrigerator. So these are similar things, heat pipe and refrigerator. If you remember in part 1, we talked about the concept of heat engine, which is used in like power cycles. The idea behind using heat engines is to use heat and generate work. The concept of a heat pump or refrigerator is the opposite. In a heat pipe or refrigerator, we want to actually pump heat from a low temperature reservoir to a high temperature reservoir. Generally, naturally, heat is transferred from a high temperature source to a low temperature source. However, in some applications, we actually want to do the opposite. So we want to pump pump heat from low temperature to a higher temperature. What are some examples? For instance, in the case of a refrigerator, inside of the refrigerator, the temperature is lower than the ambient temperature because we want to keep the food, the stuff inside the refrigerator at a temperature lower than the ambient temperature. Or another example is that, for instance, in some areas, heat pumps are used in order to keep the interior of the buildings warm during the winter. So that means that in such cases, heat is pumped from outside to inside, even though the outside temperature is lower than the inside temperature. So in summary, naturally heat can transfer from high temperature to low temperature, which we call it like cooling. However, in some cases, we want to actually transfer heat from low temperature to high temperature. Then we call this process refrigeration, and this is what we are going to talk about in this part of this chapter. If you look at this diagram, so if you look at the diagram on the left side, so here you see the structure of a heat pump or a refrigerator. It is very similar to a heat engine. It is still comprised of a source, heat source on the top, heat sink at the bottom. So that's the heat source, and then the heat sink. And then in the middle, in between, we do have a black box in general. In this case, the black box is a refrigerator. So let's look at the principle of operation of this refrigerator. Let's start from the compressor. So in the compressor, a refrigerator, for instance, refrigerant 134A, in the gaseous form, in the vapor form, enters the compressor and it's compressed. So external work is provided in order to compress the gas. Its pressure, and as a result, its temperature increases. At the exit of the compressor, at this point, we do have high temperature, high pressure gas, which enters the condenser. The condenser is like a series of coils. Inside the condenser, the heat is removed from the high pressure, high temperature refrigerant to the surrounding. And as a result, its temperature decreases, whereas its pressure is nearly constant because the pressure drop in the condenser is not substantial. So now, under this condition, we want to actually reduce the pressure of the refrigerant, and in order to achieve this, the refrigerant is passed through an expansion valve, for instance, in the form of capillary tubes. So in the expansion valve, the pressure substantially decreases, and therefore, as a result, at the exit of the expansion valve, we do have a low pressure refrigerant, but it's in the liquid form. So now it is at a low temperature, it is at a low pressure, and it can undergo another phase change process similar to the phase change process in the condenser. So both in the evaporator and in the condenser, we do have phase change processes, however, at two different pressures. Therefore, the temperature associated with these two different pressures will be different. So what happens is that in the evaporator, now the liquid wants to actually, so as it passes through the evaporator at this low pressure, it absorbs the heat from the evaporator compartment and then it evaporates. So a phase change process occurs here in the evaporator, and then at the exit of the evaporator we do have now a vapor, refrigerant in the vapor form. The vapor enters the compressor again and the cycle continues. So in this cycle, as you see, the refrigerator or the heat pump, so you can think of it as a device which is creating a refrigerated space. That's why we call it refrigerator. You could also think of it as a device which is pumping heat from the low temperature reservoir to the high temperature reservoir. So that's why it is also called a heat pump. All right. So similarly, the same concept can be applied in order to actually provide heat to another space. So in this case we call it a heat pump. So the same device, the same configuration, but the purpose is different. So in this case, the purpose is not to actually create a cold space. The idea is to actually provide heat for instance, to the interior of a house. So you could think of it this way. So for instance, if you look at the refrigerator keeps inside of the refrigerator cool, but at the same time it actually heats up the ambient. It heats up, the area surrounding the refrigerator. So you could think of it as refrigerator actually pumping heat from inside of the refrigerator and provide it to the outside of the refrigerator. So in this case, here we do have QL, which is pumped from a cold environment, for instance, from outside, and then this heat is pumped to the high temperature reservoir at temperature TH. And for this process to happen, we do need to provide heat to the compressor. And COP, coefficient of performance, is actually defined based on desired output divided by required input. In this case, the desired output is actually QH, because that's what we want to do. And if we substitute W by QH minus QL, we can find COP based on this equation, which is a little bit different from COP of refrigeration. Okay, so most heat pumps have a COP of between 2 and 3, and in some areas when the winter is not actually too cold, then heat pumps can actually be used for heating the interior of the houses. But if the winter is cold, heat pump is not a good solution for heating purposes. Instead, different forms of heating devices such as for instance resistive heaters or central heating using hot water and steam are used. Okay, so based on this, we are running out of time for this presentation. Based on this, we can define the second law of thermodynamics based on the Clausius statement. It simply says that it's impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a low temperature body to a higher temperature body. So it tells us that we cannot transfer heat from low temperature to high temperature without providing some work to the compressor. So this makes sense because heat naturally transfers from high temperature to low temperature If you want to do it the opposite, you have to spend some work and some energy to make this happen. So, and that's the second law of thermodynamics based on the closed statement. Thank you very much for your attention. This is the end of this part.